Imagine standing on a world where the horizon isn't a dozen miles away, but just a few hundred feet, where you can see the land curve beneath your feet not as a distant arc, but as something intimate and undeniable. A place where, if you felt ambitious, you could walk all the way around your planet in a single day, or jog the circumference before lunch. It wouldn't feel like a habitat, it wouldn't feel like a ship, it would feel like a world, just one scaled to human life rather than cosmic accident. That idea sounds whimsical at first, almost toy-like. A planet like a snow globe, albeit still an incredibly large one. But once you leave Earth, size stops being sacred. Gravity, atmosphere, and surface area stop being gifts of nature and become engineering problems. And engineering problems have a habit of shrinking to the minimum size that still works. So today we're going to explore what happens when we stop asking how to build the biggest artificial worlds imaginable, and instead ask how small a planet can be while still feeling planetary. From gravity-equipped asteroids to shell worlds built around micro-black holes, we arrive at a strange but powerful idea: the microplanets. Small worlds, big numbers. We tend to imagine the future of space the same way we imagine the future of cities. Bigger skylines, vaster worlds, continents wrapped in steel and glass. And to be fair, that instinct is not wrong. Humanity has never built small for long. If there's room to expand, we usually do. But if you step back and look at how civilization actually grows, not how we dream about it, but how it behaves under economics, logistics, and human preference, you see a different pattern emerge. Not one giant city, but millions of towns. Not one global megastructure, but countless homes, businesses, farms, and neighborhoods, all stitched together into something that only looks monolithic from a distance. Space won't change that. If anything, it exaggerates it. And space, the one thing you are never short of, is elbow room. The most common habitat in the future won't be the megacity cylinder or the planet-sized shell world, any more than the most common home today is a skyscraper or the default vehicle, an aircraft carrier. Those exist, and they matter, but most of civilization lives somewhere smaller. In space, that means rotating habitats the size of neighborhoods, towns, or even single extended households. Things you can build incrementally, move, sell, trade, upgrade, split, or abandon, without collapsing entire civilization. In other words, space favors houseboats. A smaller rotating habitat isn't always just a place to live. It's a vehicle, a property, and a piece of infrastructure all at once. It can drift between orbits, dock with others, cluster into cities, or peel away and head somewhere new. That mobility matters. It pushes civilization away from single massive investments and toward huge numbers of smaller ones. And that's why, paradoxically, the era of the grandest artificial worlds may also be the era of the smallest planets. Before we get there, though, it's worth grounding that intuition with a quick reality check. Imagine a rotating habitat designed not as a city, but as a home. Not a cramped tin can, but a genuine estate. Fields, forests, and space to breathe. Say, 40 acres. That's about 16 hectares, roughly the footprint of a small farm or park. In fact, it's only a little smaller than my own farm here in rural Ohio. That's far more grass to mow or forest to tend than most people want to deal with today, unless they are farmers or particularly woodsy by nature. But preferences change. In an era where robots handle most of the mowing, landscaping, and maintenance, large personal estates may well come back into fashion. We couldn't do that for everyone on Earth, though. If you divided all of Earth's land, including deserts, into 40-acre plots, you'd only get on an order of 1 billion parcels, and most households don't have 8 people in them. To give everyone land, you'd have to shrink those plots to 20 acres or less, and of course that limitation is exactly why space settlement is so appealing. In space, you can find or build more land. So while 40 acres is big by modern suburban standards and enormous by current spaceflight standards, it's not beyond the reach of a typical individual in a post-scarcity environment, especially one where machines do most of the building and upkeep. At a comfortable 2 revolutions per minute, you only need a 223-meter or 733-foot radius to get Earth gravity. Wrap a ring around that. Make it about a football field wide, 280 feet or 115 meters, half that for a 20-acre version, double for 80, and you've got a full gravity homestead you could jog around in minutes. That's less than half a kilometer across. Tiny by megastructure standards. Indeed, I'd not call it a megastructure at all, and people in the future might just call it home. Now compare that to a Stanford torus, the classic space habitat design. The Stanford torus is nearly 2 kilometers in diameter and provides on order of 160-odd acres of living area, 4 times the land, yes, but also 4 times the diameter, spinning slower in angular terms anyway, and demanding vastly more structure and coordination. Both work, both make sense, but one of them is far easier to build and mass manufacture, being smaller and needing less strength of materials, and vastly more so than an O'Neill cylinder, or our Globus' design for a Compound of One station that we like to show here so much, with quite a community in it, basically a very large housing development with attached public spaces, which is only 3 times more spacious, about 126 acres or 51 hectares. This is the core idea to keep in mind as we shift scale. Civilization doesn't just chase maximum size, it chases minimum viable size, repeated endlessly, and once you accept that, something strange happens. You realize that the distinction between habitat and planet starts to blur, because gravity does not care whether it comes from rotation or mass, it only cares about acceleration. We get ours by raw mass, 12 billion kilograms per square meter, or 1.2 million tons per square foot, which is a lot more than the typical 1 ton per square meter or foot, depending on how thick you want your dirt, that we imagine for your typical rotating space habitats. The thing is, there's a lot of mass we would want to store that isn't very useful for primary construction, like hydrogen and helium, which are extremely abundant and ideal as fusion fuel. That naturally leads to the idea of enormous fuel depots, so massive they can hold themselves together with their own gravity, so it cuts down on leaks. Add a solid surface layer on top, terraform it, and you've got what we call a shell world. These would never be the majority of your living area, but they would be pretty common, since in a fusion economy, the gravity well of Earth-mass planets isn't that big of an energy tax for storing fusion fuel, around a millionth of the energy it contains, and really helps prevent loss to leakage for very long-term storage. And there's a deeply unintuitive result hiding in that fact. If you want Earth-like gravity at the surface, the amount of mass you need scales with the surface area, not volume. Make a world half the radius of Earth, and yes, it's far smaller, but each square meter of ground still costs the same gravity-producing mass as it would on a full-sized planet. That means there's no inherent gravity penalty for bigger or smaller worlds. You don't save gravity by going big, you don't lose it by going small. And once you contemplate that, a radical idea becomes almost unavoidable. Why not build a planet bigger? Saturn's a big gas ball, the least dense planet, with about the same surface gravity of Earth already, and you could have a planet 100 times more spacious than Earth with one. The mass per living area stays the same, but the density inside goes down, inverse to radius. Twice as wide, half the density for the same surface gravity. That's where microplanets come in, and also the core problem with them. If you want Earth gravity at the surface, shrinking a planet means increasing its density. Cut the diameter in half, you need twice the density. Keep going and the requirements rise fast. So what to make it from? The densest ordinary matter we know of, osmium and iridium, top out at only about 4 times Earth's average density. That means using normal materials, the smallest Earth gravity world you can realistically build is roughly moon-sized. Anything smaller demands densities we simply cannot achieve with conventional matter. And even then, those metals are extraordinarily rare and valuable. Using them as a bulk planetary mass would be like terraforming the surface of an enormous iridium vault. Impressive, yes, but wildly impractical. Which is why planets get big so quickly and why replacing planetary mass with something far more compact changes the game entirely. Now, ordinary black holes do not help us here. The smallest naturally forming black holes are stellar mass objects, roughly 3 times the mass of the Sun, which would give you a world about 1,000,000 times Earth's mass and surface area, a literal megaplanet, and the origin of that episode's name. Interesting in its own right, but it's the opposite of what we want today. What we're really after is high density without high mass. White dwarfs, neutron stars, and black holes all achieve that kind of compactness. But white dwarfs and neutron stars only exist at enormous mass, and there's no realistic way to keep them stable if you try to scale them down. Their physics simply does not allow it. Probably, you might be able to do it through extreme magnetic compression. And this raises another option. Stellar cores point towards a potential middle ground. Our Sun's core is about 150 times denser than water, roughly 30 times Earth's average density. In principle, you could magnetically confine matter at that density, essentially turning into a controlled fusion plasma, and so you could build a planet about 30 times smaller in radius, with roughly 1,000th of Earth's surface area. Now, that's not quite a microplanet, it's more of a milliplanet, but still an intriguing concept. More massive stars push this further. During helium burning, especially in later stages burning carbon, neon, and oxygen, stellar cores can reach densities tens of thousands of times to millions of times that of water. That would allow truly microscale planets, if you could hold that material together without stellar mass. And here's the catch. Fusion at stellar timescales is incredibly weak. Spread across its mass, the Sun produces less than a milliwatt per kilogram. Red dwarfs do even less. By comparison, a household generator puts out tens to hundreds of watts per kilogram. Commercial fusion would need to run vastly hotter and faster than stars do, not slower. So if you could magnetically confine matter at stellar densities without requiring stellar mass, essentially decoupling density from gravity, you get both a power source and a gravity source in one package. It wouldn't even need to be spherical. A donut-shaped tokamak reactor could generate gravity just fine, as long as it stays small compared to the planet itself. Even then, the planet does not need to be a perfect sphere. There's nothing sacred about that geometry, and there are some fun alternatives. If you can make that work though, you then also need a sweet spot of overall density to energy output, as you will keep raising the power-to-mass ratio as you raise density. Denser matter fuses faster. But you don't want to exceed what will keep your planet warm and lit. You don't have to limit your core to hydrogen and helium either. You can mess with fusion rates, slowing them while raising density by introducing other common elements like neon or even iron to tweak things until you have the Goldilocks zone of density needed for the microplanet you're trying to build with the power output you need to avoid burning everyone living there. This can probably be done, but if you can't pull that off, there's one object that has no trouble confining itself at any density or any mass scale: a black hole. If we can manufacture them, a topic we discussed many times, then we can set their mass almost arbitrarily, feed them slowly, and they become a long-term power source as well as a gravity generator. It would take eons for them to grow enough to noticeably change surface gravity, so any remodeling happens on geological timescales, not human ones. What is a microplanet and what is it like? So that brings us back to what a microplanet actually is. A microplanet is not a shrunken Earth in the conventional sense. It isn't a rocky ball with a molten mantle and a fragile atmosphere clinging on by sheer gravity. Instead, it's an artificial world whose gravity comes from a compact mass source, often a small black hole, surrounded by an engineered shell that provides the surface, the landscape, and the sky. From the ground, it feels planetary. You walk on curved horizons. Gravity pulls straight down. Rivers flow, weather forms, and buildings stand upright without spinning frames or Coriolis effects. Or at least different ones. But structurally, it behaves far more like a habitat than a natural world, and crucially, it has to. A small planet with Earth gravity at the surface still won't hold an atmosphere the way Earth does. Gravity drops rapidly with altitude when the radius is small. On these microplanets, a kilometer up, gravity is already noticeably weaker. A few kilometers higher, and it's a fraction of the surface gravity. Left open, air would thin, escape, or behave nothing like Earth's atmosphere. So instead of fighting that, microplanets embrace enclosure. They wear a shell. That shell does not need to be thick or opaque. It can be transparent, segmented, reinforced, and layered with radiation shielding and structural support. This crystal sphere or patchwork of domes around your microplanet holds the air in without interfering with the view. So it holds the air in, sets pressure independently of gravity, and decouples climate from planetary size. It also solves problems Earth never had: micrometeoroids, solar flares, orbital debris, and long-term atmospheric loss. And a small puncture or even a fairly large one does not mean all the air goes blasting away. There's still gravity, and we have tons of fixes for dome damage that apply, even quick ones or major holes. If you're worried about ruining the view, remember this: at planetary scales, thin supports fade into visual insignificance. A faint tint overhead, not a ceiling. The sky remains the sky. What you end up with is something that sits between worlds. Not a spinning ring, not a natural planet, something new. A planet you can build in batches, expand in rings, duplicate by the thousands, and scatter across the star system. And that brings us back to economics. If most people do not live in megastructures but in small habitats, and if planets themselves can be made modular, enclosed, and scalable, then the future may not be dominated by a handful of colossal artificial worlds. It may be dominated by millions of tiny ones, worlds built not to impress but to live in. So, could you buy one? Well, that depends. In a true post-scarcity economy, individual people might own something as large as an entire neocylinder, but also have access to astonishing virtual landscapes, private spacecraft, and effectively unlimited personal space. What really matters is not the theoretical maximum, but what people would actually want as a place to live day to day. Somewhere you can go for a walk. Somewhere that feels like a place, not a project. That's one of the quiet advantages of both microplanets and rotating habitats. You can walk in a straight line and eventually end up back home. Micro, of course, just means small, but like mega, it's also a metric prefix with a precise meaning. A micro-Earth, taken literally, would have 1/1,000,000th of Earth's surface area, about 1,000th its radius. We could obviously go smaller or larger, but in this specific sense, we're talking about a world with roughly 500 square kilometers of surface area, about 200 square miles, 50,000 hectares, or 126,000 acres. That's room for several thousand of these 40-acre households we talked about earlier. In scale, that's comparable to an O'Neill cylinder or a smaller US county, especially the compact ones along the East Coast, not sprawling places like my own Ashtabula County here in Ohio, which is about 7 times larger if you count the lake, and still several times larger even without it. Out west, of course, counties get bigger than some countries. From a construction standpoint, this scale looks very plausible, but also raises a practical question. How usable does it feel? A micro-Earth like this would be about 8 miles in diameter, with a circumference of roughly 25 miles. That's not something you can casually stroll around after dinner, but it's something most people could walk around in a day if they needed to. On a bicycle, it's trivial. For anyone even modestly augmented or transhuman, it's barely an outing. And at this scale, a lot of things start working in your favor. You have plenty of vertical room for a deep atmosphere and genuine and natural feeling weather. The planet only rotates once per day, so you don't get strong Coriolis effects or fast-moving storm systems driven by rotation. The surface speed is only about 1 mile per hour at the equator. Weather would not organize itself the way it does on Earth. But that's not a flaw, it's a design choice. You could wander nomadically and stay near the Terminator, always living in twilight, or stick to permanent daylight or permanent night if you preferred. Maybe live in a houseboat on a world-spanning lake that you simply slowly drift around to stay forever in the daytime. You could rely on natural sunlight, artificial lighting, or a mix of both. You'd almost certainly want a decent-sized reactor and thermal system to move heat and water around, shaping climate intentionally rather than letting it emerge by accident or needing high-powered mechanical intervention. And as these worlds get built by hundreds, thousands, or millions, you get very good at this. Landscape wouldn't just be decorative, they'd be functional. Grooves, ridges, forests, and outcroppings could guide airflow, trigger uplift, or break up wind without massive active pumping. And the ceiling itself, transparent, segmented, and engineered, could play a role in shaping weather rather than just containing it. At that point, climate stops being something you endure and becomes something you tune. Not perfectly, never perfectly, but well enough that a small world can feel as rich and alive as a large one. And that's the real theme here, not building the biggest possible world, but building worlds that feel right at human scale. So, could you go even smaller? Yes, especially if you're willing to live inside a proportionally larger atmosphere. Instead of a thin skin of air clinging to the surface the way Earth's does, you have an atmosphere whose scale height is comparable to the radius of the world itself, or even bigger. At that point, the transparent shell enclosing the planet becomes much more important. Without enough air depth, you lose the familiar twilight gradients, the reds, golds, and blues that come from the light bending through a long atmospheric path. Go small enough and you could also lose true clouds altogether. That's not unique to microplanets, it's the same issue we face on small rotating habitats. We already know how to fix it, or at least some options for doing so, with thicker atmospheres, engineered lighting, and carefully shaped ceilings. And the upside here is that you still get straight down gravity, without your neighbors ever being overhead the way they are in rings or cylinder habitats. In terms of mass, these worlds still scale the same way as the Earth-like planets. You need roughly the same gravity-producing mass per square meter of surface, and that mass has to come from somewhere. In practice, you'd likely feed them hydrogen or helium skimmed from gas giants or stars, materials that are abundant and not especially valuable for fusion fuel. And for the black hole itself, in our example microplanet, the one about 8 miles across, it would have roughly 1/1,000,000th of Earth's mass. Physically, that black hole would only be about 18 nanometers wide, roughly 300 times the diameter of a helium atom. Feeding it matter is straightforward. You don't need anything exotic like a Kugelblitz generator to keep it alive. A black hole this massive but this small does not automatically mean dangerous tides. What matters is your distance from it, and your planet's radius is enormous compared to that hole. Just don't stick your head into it. And I would bet on an inner filling of helium or maybe even air at a density appropriate to keep it as a fairly hot gas that can push back against the shell your land is on to lower required structural strength. Depending on temperature, you might be able to go flying around in it, though that strikes me as needlessly dangerous, so presumably lots of people will do it. The black hole will barely touch that matter either. It would take eons to gain much mass, without careful effort to aim atoms right down its tiny gullet, especially as its Hawking radiation provides outward pressure. It's small at that mass, but it's a small spot it's affecting too. Its Hawking radiation would correspond to a temperature of around 20,000 Kelvin, putting the peak emission in the ultraviolet around 7 electron volts, the nastier end of UV, the sort Earth's atmosphere already protects us from. But critically, it would only be radiating on an order of 10 microwatts. Energetic, yes, but so faint as to be effectively harmless. And with a lifetime measured in billions of trillions of years, feeding it for power would only extend that lifespan further. You keep this centered by magnetic fields or streams of matter you're running into it for power, so your black hole does not slowly drift off. You could embed one of these black holes in the center of a large asteroid, imported from some distant black hole factory and fed cheap mass along the way, but I suspect that wouldn't be the preferred approach. Imposing full Earth gravity on a natural microgravity asteroid would likely tear up its internal structure and erase the very landscape you might want to preserve. A better approach would be to start with a smaller asteroid, install a metal framework around the black hole, grind the asteroid down, and rebuild it around that core. Add your shell, water, and atmosphere, then sculpt the surface deliberately. Presto, a terraformed asteroid. Although there's a lot of other options, and we should probably do an episode on it. Today we're talking about building entire artificial worlds, microplanets powered by black holes. Ideas like that sit right at the intersection of physics, engineering, and imagination. A show that explores ambitious engineering ideas in the modern world is Practical Construction from Practical Engineering. It walks through how massive infrastructure projects are actually built. Tunnels, bridges, flood systems, and surprising complexity hiding behind structures we usually take for granted. And for deeper speculative ideas, I also released Nebula exclusives like Lazarus protocols, where we explore how civilizations might design practical backups to survive catastrophes. Those are both on Nebula, where every episode of SFIA, over 800 episodes, premiere early and completely ad-free, and it also has our audio-only podcast content, also ad-free. Use my link with a QR code to get 50% off an annual plan, just $30 for the whole year, which would be less than 4 cents an SFIA episode, not to mention all the other content from a galaxy's worth of awesome creators. And it's worth remembering that this is actually where the term terraforming comes from, too. The word was coined in Jack Williamson's story Collision Orbit, which involved giving asteroids enough gravity to support seas, skies, and human life. By that original definition, adding gravity to an asteroid so it can hold an atmosphere absolutely counts as terraforming. Of course, you have some other way of stabilizing degenerate matter or generating gravity artificially, as classic science fiction often assumes. You could use that too. Though I'll always note that a gravity generator probably needs power to run, which makes it odd that starships in fiction lose power and life support simultaneously, yet nobody starts floating around. That's probably more for limited special effects budgets than imagination, though. They also make BWC megastructures more likely. As a reminder, because we can, megastructures are things like disk worlds, cube-shaped planets, donut worlds, and other deliberate exotic designs, built less out of necessity than novelty, curiosity, or simply desire to prove they can be done. These use the same engineering principles as full-size worlds, but are vastly easier to build when scaled down, and require far less material. As a result, you might see something like a 20-sided icosahedral microplanet, with each face owned by a different family. A D20 world. You wouldn't see your neighbors any more than you would on a spherical world. There's still a horizon, but now you'd have to go all the way to your property line to glimpse the edge of someone else's domain. In fact, your own side wouldn't even have a shaped horizon anymore. Most people would still shape the terrain with hills and dips, much like we expect in rotating habitats, to soften or disguise the subtly un-Earth-like geometry, even if gravity still points in the right direction. Microplanets sit at a fascinating intersection between habitats and worlds. They let us keep gravity, skies, weather, and horizons, while abandoning the assumption that planets must be rare, massive, and immutable. Whether built around black holes, stellar density cores, or technologies yet to be invented, they point toward a future where worlds are designed, duplicated, and customized at a human scale, not monuments to impress the cosmos, but places meant to be lived in. And if the future really does belong to small things repeated endlessly, then the galaxy may one day be filled not with a few grand artificial worlds, but with millions of tiny ones, each just big enough to call home.